Okay, I want to say a few words about operations and relations. So now the strategy should be the following. So it's hard to compute this vertex algebra from either moduli spaces, as we discussed last time, or a few days ago. And sometimes you can carry out this procedure of physics calculation of the full CFT, and then of course you get the vertex algebra. That's good, but you cannot do it for any four manifold. And the idea is that, but you can nevertheless build any four manifold and three manifold by cutting and gluing basic pieces. So those of you who have children, you know that your kid may have a Lego, and Lego has very primitive pieces. So there are pieces of very fixed type. There are finitely many of them, very small. But then if you have lots of these pieces, you can build a very creative structure out of it. And there are lots of structures which you can build with very basic pieces. So the idea would be, and in fact in topology the idea is the same, that three manifolds and four manifolds however rich they are, and we don't know, for example, classification of smooth four manifolds, but we do know they all can be built out of finitely many small pieces, including such D4 or C2 that was one of the basic examples. In order to build generic four manifold, you need a little bit of more Lego pieces, just a couple more, but again, it's a very small finite set. So the idea is to start doing cutting and gluing. So cutting and gluing, or equivalently operations and relations. So the idea is that you can build same manifold in number of different ways, and this should be reflected as equivalences of vertex algebras. The result of corresponding operation on the vertex algebra should also give the same result if you get the same manifold out of different ways of gluing things. So in general, one general statement is that upon operation which is very natural in four manifold topology, you can take four manifold and take a connected sum with any other four manifold. What this means is that you remove a point of a four manifold or small neighborhood of a point. What you produce is a boundary which is a three sphere, and if you do the same on the other manifold and glue them along this common three sphere, you get a new four manifold which has no boundary, and that operation is called connected sum. So for example, you can take connected sum with CP2, or you can take connected sum with CP2 bar. So these operations are called blow-up, or in the case of CP2, generalized blow-up. So usually this one is called blow-up. In the case of plumbing diagram, how it's represented is basically you take your original plumbing diagram and then put an extra dot, which is sitting in a vacuum, not talking to anybody, and is carrying, say, plus minus 1, depending on which one of these you choose. So again, this plus or minus 1 is the self-intersection on one generator of the second homology of CP2 or CP2 bar. So a natural question is, what do you get? In both of these cases, what is the corresponding operation on vertex algebra? Very generally, if you take this operation of connected sum, vertex operator algebra behaves as so connected sum is the simplest operation in the world of manifolds, and it corresponds to simplest operation in the world of vertex algebras, namely you take a tensor product. Nothing really interesting happens. So here, the result can be expressed in terms of VOA of original four manifold M4 tensored with some fixed algebra, which has a name U bar, and in this case, it has a name U. And this is the algebra which, in the case of U, that was identified in joint work of Boris and Misha with others and called UROT. But you have two versions of this algebras corresponding to CP2 bar. It's U without a bar, and for CP2 without a bar, it's U with a bar. So we have to blame them for this notation. The reason is that usually this the second one is called blow up, and that's that they really studied and identified that guy. So since it appeared, they didn't give it a name with a bar, that would be extra notation. But now, if you really want to consider them in parallel, you're only left with a choice that you have to use U bar for this kind of. Sometimes we call this anti-UROT, or anyway. So using the same business and knowledge about the CFT, which in some cases is computed, and for example, central charge is known in general, you can quickly ask yourself what happens to the central charge of your vertex algebra when you do this blow-ups, or you take this connected sums with CP2 or CP2 bar. I gave you a general formula before, and the only thing that happens is that you increase your early characteristic by 1, and you increase a signature by either +1 or -1. So therefore you can just plug the numbers into the general formula and quickly learn that C left of U has to be -5, and C left of U bar has to be +31. In fact, those of you who already have your your notes with the general table can easily see that that's indeed the case. Moreover, you can ask how this works. So this is for in both cases for G equals SU2. So natural question then is what is the algebra U bar? And moreover, if you're ambitious and already know the answer for U and U bar, you can ask, okay, what is the right moving sector? So what is the corresponding CFT, namely including the right part? So here we're talking about vertex algebra.
It's really tensor?
Yes.
Extent, not extension.
I believe in the case of CP2 and CP2 bar, just a tensor product. Yeah. But again, here I have to resort to experts. At least for SU2, I believe, and I think in general people expect that it's a tensor product. So question is, what are these guys? What is this U? What is U bar? And corresponding maybe full CFT. So in the case of SU2, we know what U is, but again, physics says that there is more work to be done. So for instance, you can start there in G and ask for corresponding algebras U and U bar for not just for SU2, but for SU3, SU4, SU5, and so on. And here I'm just going to list central charges, focusing my attention on U, which was roughly SL2 at level 1, kind of skewed, as Misha explained in his lectures. So here are the central charges -5. That's what we already discussed before. But there are analogous formulae for SU3, SU4, and you quickly compute that here it will be -22, -57, -116, and so on and so forth. So the challenge to the audience, or homework to all the students here, is to construct this algebras U and U bar for SU3, SU4, and so on. I don't know what they are, so maybe somebody knows. But so that has to be that's one simple implication of this general analysis. So now I want to give you another class of examples, so that you don't get the impression that everything is produced by extensions. This other class of examples also contains 4 manifolds of special type, just like the toric manifolds that we discussed here. And
this phenomenon of change of orientation, what is this doing with U and U bar?
Yeah, so morally what's happening is that it's a non-trivial operation. Yeah, it's not easy to say, of course. Morally what happens is that the self-dual and anti-self-dual classes on 4 manifold contribute to left and right moving sectors of this 2-dimensional CFT. So in some sense, therefore, naively, what is expected is that the fact that here you have positive self-intersection will make a contribution to the right moving sector from this 2 cycle. And here it will go to the left sector, which is our VOA. But again, this is very heuristic thinking, whereas in each case it has to be really analyzed carefully. So this operation of switching orientation is not entirely obvious. Yeah. Partly because the sectors are not...
It's not on counting for one of them. It's fine for other one that do not exist.
And exactly. So that's why, or it in fact, it's precisely this phenomenon of false and mock that will appear, hopefully will appear soon. Yeah. So indeed, as Boris points out, the two sides are very asymmetric, and they have to do. So indeed, there is something deep going on here that, from the viewpoint of PDEs or instant-on counting, B2 plus and B2 minus of the story. So B2 plus, and I'll write it in this order: B2 minus of M4 and B2 plus of M4. A priori, you could expect that they're kind of symmetric. I mean, what's the big deal between self-dual, anti-self-dual two forms? They should be symmetric. But they're hugely not. So what I'm trying to say is that in this conformal field theory, what happens is that these guys become left, and these become right. And these two sectors are already asymmetric because this is this contains superversor, this is just non-supersymmetric. So they are quite different. Also, if you do the instant-on counting or solve other PDEs, if you gauge theorists, you also know that, in fact, B2 plus and B2 minus are not on symmetric footing, not at all. So in one case, you get something nice and well-behaved. In the other case, you get something quite different. So this phenomenon is not fully understood, but it's good to keep in mind that there are indeed rather different beasts somehow. But anyway, again, it's a philosophical remark.
Can you say about U? It is more or less one boson wrote structure, but
yeah.
What is about U bar? What is the size of its representation? How many bosons?
I don't remember. So this is one of the instances where I have to resort to Boris. I think we try to say as much as can be said. It's definitely in the paper, but I don't remember.
Is it related to SL2 in the level minus 1?
I forget, maybe.
Yeah, I definitely don't remember, but everything that can be said is there, but it's very limited. So
This question appears.
okay, so in previous discussion, the mantra again, which I learned from Boris, was that gluing can be done at least at the level of vertex algebras if it's kind of generic in two ways, either by extensions or BRST reduction. So we talked a little bit about extensions. So next class of examples will involve gluing basic pieces, this Lego pieces of 4 manifold, gluing M4 from basic pieces via BRST reduction at the level of vertex algebra. And the examples that we'll see in this class of examples will be of the type where 4 manifold is also the one we considered earlier. It's CP1 cross Riemann surface of genus G with n open ends and holes. And every such, so here gluing is a natural thing. You just represent Riemann surface by gluing basic pairs of pens like this via cylinders or tubes, or simply by identifying the boundary. So in this case, there is a very nice work of, I hope I can find it, of Pavel Putrov and some other people. So let me try to find at least an archive number so I don't leave you completely. So you can find it on the archive 1505 07 110. Where they actually determined the full CFT. So previously, in previous hour, people were asking me, do we know the right sector? So here I'm talking again about mostly SU2, but I don't remember if they did SUN case or not. But for SU2, the answer will be especially nice and simple. And this is the case where actually you can say what is the full two-dimensional conformal field theory, including both left and right sectors. So I'll give you therefore two answers to both of these questions. What is the full CFT and what is the VOA? And in the case of VOA, the answer will be that we have to find the Lego piece for this building block for a pair of pens. Then connecting these things will be VRST reduction. And each of these pictures, of course, assumes that this is, say, cylinder times CP1 or a pair of pens times CP1. So you glue manifolds out of these basic pieces.
So such kind of manifolds are special from your Galvanometer.
Yeah, so these are precisely special. That's what.
But still, you can, in this special case, it's also machinery how to predict the central charge.
Yes,
no?
yes, there is. It's some modification of the general formula. So that's what these guys did. But again, not only they did use the full.
So they have some prediction and then construct the algebra.
Yeah. So in fact, what happens is that this. So since you asked, this two-dimensional CFT that we call T of M4, actually in this case has also enhanced supersymmetry. So previously it was 0 on the left, it was just usual Virasora, and n equals 2 super Virasora on the right. But here it enhances to n equals 4 super Virasora on the right. So it actually, just like holonomy is very special, then it's reduced. So is property of the supersymmetry here. It's also enhanced. And
only in the right sector. In left sector, no supersymmetry.
Correct, yes. So in this case, what happens is that at the level of full CFT, a pair of pens corresponds to, so in general, this the CFT is n equals 0, 4 sigma model. So it has a geometric description whose target can be constructed by following simple operations. So you first associate a target space to a pair of pens, and you take a target to be C2 times C2 times C2. And think of this as a representation 2, 2, 2 of 3 copies of SU2. So of SU2 cross SU2 cross SU2.
Maybe you need arrow instead of equality.
Well, I really mean equality, why not? So I mean that this piece of the geometry times CP1 corresponds to this piece of the target space of the sigma model. And then, so this is some huge space, but then every time you do the gluing, you perform hyperkähler quotient by corresponding SU2. So for example, here I have SU21, SU22, SU23, and you should think of them as SU21, SU22, SU23 seating or associated with the boundary components. And every time I want to glue this to something else, I take product of the target space, this factor and the other factor, and then do SU2 hyperkähler quotient, which acts on this as a two-dimensional representation, and whatever else gets glued to it, some other pair of pens as another two-dimensional representation, and so on. So what I get as a result is some interesting hyperkähler quotient construction of a target space, which is quotient of basic hyperkähler space by a bunch of SU2s. So as a result, the vertex algebra is also easy to say. It basically becomes beta gamma system. So BRST reduction is remnant of this SU2 quotient, or vertex algebra manifestation of this quotient. And this piece is basically beta gamma system associated with same space, basically C2 tensor C2. So this is nice vertex algebra, and it appeared before, or almost at the same time. In fact, it's funny because I think this paper of Putrov, which appeared in 2015, was developed in parallel with other constructions, where people sometimes start with 4D n equals 2 four-dimensional conformal field theories. And remember, last time we talked about such things, so we talked about Coulomb branch of such theories. And I told you about work of Dupay and our work with Nakajima, where you can associate a modular tensor category to a Coulomb branch. But then another interesting element of this four-dimensional theories is Higgs branch. So they have two interesting, what people call branches. So again, these are some physics words or jargon. Higgs branch. And to this, we can actually associate a chiral algebra or vertex algebra by taking Q cohomology very much like what we discussed today, but it's a very funny Q operator, which people construct out of superconformal charges in this case. So it's very strange. It's not just the usual Q. So in fact, interesting part of their work was finding.
What is the logic? That we have four-dimensional manifold and this n equal to theory, yes?
Yeah.
And then it is something to what is calling this Coulomb branch and Higgs branch.
Mm-hmm.
Yes, and this reduction is construction of one of them.
Yes, so it appeared
in a special case when manifold is
exactly
certain times 2.
right. So what happens is that for special class of theories labeled by Riemann surfaces associated with such genus G Riemann surfaces, possibly with punctures, you can construct Higgs branch, and it will be precisely this target space. So it will be, in our class of examples, target space of VOA of M4. I mean, for this, I'm still considering this class. And the vertex algebra will be precisely the VOA of M4. So here, there is a...
But this Higgs branch exists for such kind of manifold, or it's generic things?
No, Higgs branch is the general property of this 4D n equals 2 theories. It may be empty, it may be single point, it may be something else, but it's always hyperkähler manifold, and so is the Coulomb branch after reduction on the circle.
Construction with sigma model, or just it is some Poisson or symplectic, and then we cook up vertex operator from that.
Correct.
How
yes.
general this is?
No, this is just nice, neat class of examples. So this story has life of its own. In fact, this is going to be, I believe, the subject of Arakawa-san. And I just want to say that it has funny, interesting overlap in this class of examples. I'm not saying that this VOA-FM4, in general, this is labeled by 4 manifolds, and this is labeled by 4-dimensional theories. So they're labeled by completely different data. And it's very funny that in some class they actually coincide. Maybe it's not surprising because we know very little about vertex algebra, so it's not surprising that those examples which we know about appear sometimes in different contexts. And I don't know a physical connection between them. In part because notice that I'm still talking just about this class of examples, very limited territory. But even here, even though these algebras coincide and these moduli spaces coincide, associated varieties, this story, remember, has an upgrade, which is the full 2-dimensional CFT. So in particular, this is this theory T of M4. So it has left and right sectors. And in this story, with the Higgs branch, because this vertex algebra is constructed in a very funny way, it doesn't have right sector. It cannot. In fact, the physics construction is such that it's really chiral. It's really only holomorphic part. So therefore, initial question is, even in this class of examples where there is this funny overlap, does the right sector, so I'm basically now echoing back at the audience, same question Sasha was asking me before the break, what is the meaning of the right sector for this Higgs branch and vertex operator algebra associated to a Higgs branch? I don't know. And another intriguing observation to connect the dots with something I told in the first or second lecture is that now there is also yet another connection. So we're starting making a bunch of relations. There is a relation between this tensor category and vertex algebra, or this.
But at least we expect this right-hand side for this vertex algebra.
Which one?
For this one.
In this class of examples, so what I showed is that they're equal. So I told you what this is, and just by construction, hopefully, again, Tamayuki will explain.
It has the same in this special case.
Yes, yes. In general, absolutely not. They cannot be the same.
But anyway,
yeah.
we expect to have right hand.
Yeah, right hand side, you mean right moving sector. Yes, 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 yes.
And
yeah.
we don't know what.
In this case we do, because we can describe this full CFT as a sigma model with hyperkiller target space. So in this case we actually do know what it is. So these guys describe the full, so that's one of their instances where not just VOA FM4 is known, but the full CFT is known. And again, it's
what is this? So here you may have some kind of reduction of this bosonic system and so on. And if you want to construct n equal 0, 4,
yeah.
what to do?
It's you can give different descriptions of right moving a sector. It always has to have n equals 4 supervirasora, obviously, and you can say that it's use the sigma model language and say that it's chiral DRAM complex associated to this quotient, hyperkiller quotient target. But then again, you have to realize n equals 4 in there.
But it has really similar construction. You take this boson, then
it's exactly this construction. Yeah. So it just includes fermions, which make it supersymmetric. But it's at the level of target space, it's exactly that. It's well known that if you have a sigma model with hyperkiller target space, you can make this n equals 4 supersymmetric. And basically, this is precisely the right moving sector here. Yeah. That's what I said. I don't know. I don't remember what exactly these guys did. I remember they did SU2, maybe something for SUN. So, yeah, that's a good question. I don't remember. I think it probably cannot be much better than what we have in this story. But
you know something about right sector for your algebra?
No. Hopefully to him it's new. So that's why I'm hoping that it's something useful and interesting. Yeah. Because morally, I mean, the way this algebra is constructed, as hopefully Tamayuki will explain to you, it's Q cohomology of something, but you cannot say where this algebra really lives. There is no two-dimensional space in this four-dimensional theory where you can say, okay, it localizes to that 2D space. That's not, unfortunately, that's not the case. And therefore, there is no 2D space, there is no left or right for that space. It's only chiral. Yeah. But anyway, it's a nice observation. They coincide, so there is a right sector here as well. And this is expose of the second class of examples where, again, these algebras can be computed. And hopefully you see the rules of the game that in many of these classes, you break your basic manifold in pieces and then try to glue these Lego pieces together in one way or the other. So what I want to do next, and this will be my last stopping point and conclusion, is come back to plumbing graphs, which we just saw before the break, and play with them a little bit and tell you about something that's really novel and one of the surprises which I cannot fully explain. So the goal of most of which happened today was to explain that computation of Seiberg-Witten invariants, which gives correlators and VOA, and Vafa-Witten invariants, which gives characters, should not be a surprise. So from this point of view, it nicely explains why this happens, and moreover allows to make predictions for such things. But next I want to tell you something which is only partial explanation of the surprise, I believe number 2 on my list, for which I don't have a full explanation. And I think lectures are supposed to end on some note which is not fully resolved, so that we have appetite for coming back and understanding things better. So this is precisely such a subject. And the idea is that once you understand simple planning graphs, as we saw earlier today, of the type, say, A1, A2, A3, and so on. So this is a linear planning graph that we encountered, and we built vertex algebras. So you hopefully have an idea of a 4-manifold that you build in this way. So you build a 4-manifold which has B2 equals n. It has exactly n 2 cycles represented by these dots. It's non-compact, and these 2 cycles have intersection form given by the linking matrix of this graph. So it's adjacency matrix such that every time you see, I'm going to call it Q, every time you see a vertex, you put AI in a diagonal position. So A1, A2 will be sitting on the diagonals, AN, and every time you have 2 vertices connected by the edge, you put 1 in the position ij. So it's literally a linking matrix of this graph. So in this case, for this example, it will have 1s in subdiagonals and 0s elsewhere. So, but so it's a 4-manifold which has H2 of M4 with integer coefficients has this intersection form, and B2 is equal to n. It's non-compact, so just like all these resolutions of LE spaces, which have, for example, -2s here and blow-ups that have -1s that are really special cases, it's a non-compact space. It's glued out of charts of C2, but it still has a boundary. So it makes sense to ask, what is the boundary of this 4-manifold? If 4-manifold is non-compact, its boundary is going to be a 3-manifold, and it's going to be compact. So therefore, same planning graph, for example, this one, now more general, with labels A1, A2, A3, A4, and so on, such that all labels are integers, defines for you several things at once. It defines, first of all, non-compact four-manifold, which if you want, you can compactify further, that's something else. Or it automatically gives for you compact three-manifold, which is the boundary of M4. So you can use same graphs called plumbing graphs. To label both of them. And if you don't know anything about three-manifold or four-manifold topology, you should think of the world of four-manifolds and three-manifolds roughly represented by arbitrary graphs you can draw with loops and anything you want. As many dots, it could have, for example, 15 million dots connected in various ways, just like Facebook social network. I mean, there is a four-manifold for connectivity graph of Facebook, I'm sure. So it's a big universe of possibilities, and if I were to give a crash course in 5 minutes what four manifolds are labeled by, this would probably be my best answer. And the same for compact three manifolds. So just to give you a couple of...
Sorry, but I heard something like that diagram, it can be, you can make a like topological manifold, but it doesn't have.
Correct. So that's yeah. So this is it depends in what universe. Yeah. So that's where I'm suppressing something delicate, which it's a correct statement about compact form manifolds, in fact. So what I said in passing that you can, I said briefly that if you want, you can compactify. And this statement requires some caveats in precisely this kind of questions, and whether you want topological or smooth. So this is where things are really interesting, and I'm not going to do that. But in the world of free manifolds, there is no such subtlety, so that's where I'm transitioning next. So I want to spend the last 15 minutes just on free manifolds. And use the same data as encoding both. So it's a nice bookkeeping device, and it's very efficient. So I can teach you both 3 manifolds and 4 manifolds right at the same time, because they're labeled by the same data. So, in fact, let's take your example, E8, which will be given by E8 linking diagram. So I have to assign the labels. In this case, I'll make a choice that all of them are -2. And this is going to be, as a 4 manifold, some non-compact 4 manifold. In fact, it's really nice space. You can think of it as a resolution of singularities and so on. But the boundary of that 4 manifold is a compact 3 manifold. In fact, we encountered this earlier. This is precisely, in this case, M is Poincare here. Also sometimes written as sigma 235. This is notation that people use for so-called Breeze-Korn spheres. So another example is to take the graph to be just the simplest one. So simplest graph is the one which consists of a single point. We use this single point not connected to anything to denote blow-ups and blow-downs. In that case, they were labeled by ±1. And if I ask what is a 3 manifold associated to such dot labeled by ±1, it will be a 3 sphere. But if I allow this to be any number p, or a, which is integer, then it's going to be S3 mod ZP, also known as a length space, and so on. So there are lots of examples you can build out of such graphs, and some of them are familiar and some are not. So, given this data, in the remaining 10 minutes, I want to define for you a class of functions associated with such graphs, or equivalently associated with 3 manifolds and 4 manifolds, which are defined by simple rules. I'm not going to tell you where these functions come from, but the idea will be that if you have a graph of this type, I'll produce for you a collection of functions, which I'll call Z hat, which will be a Q series, and my job is to give you a prescription how to construct this Q series and tell you a couple of things about their properties. And properties are going to be nice. That's why I'm talking about this in the first place. So there'll be also additional label and so on. So this will take values and Q to some delta Z of Q. And the rule will be exactly illustrating the strategy of Lego pieces. We will decompose everything into basic pieces, and then we'll combine it together. So in fact, this thing will be given as multiple integral over variables which I'll call ZV, or maybe Zi or Zj divided by Zj. So product over J taking values in the set of vertices. So what I'm going to do, I'll introduce one complex variable for each node, each vertex in the graph. And then I'll construct and I'll give you some universal factor that we associate to every vertex. Then I'll have analogous contribution from edges. So if ij belong to a set of edges, we'll have another second Lego piece here for every edge that we see in the graph. And then I'll also take a theta function associated to this linking matrix Q. So remember, I just erased what Q was, but Q is essentially connectivity matrix of the graph. It has AIs on the diagonal and zeros and ones telling us how edges are connected. And this will depend on variables Zj and Q, so it is what you think it is. It's basically sum over lattice with the quadratic form Q, capital Q, such that little q is raised to the something quadratic expression in terms of lattice vectors, and z is raised into linear thing. So it's sum over n's, vector n, q n, q n, z to the n. It is what you think it is. Okay? So now I have to tell you only two things. What are the basic building blocks for Lego pieces for vertices and edges? Namely, what do I have to take product over? And I have to tell you what is the contour of integration. So it's kind of clumsy, so let me maybe put product over vertices here and say that contour of integration is easy. You just integrate on unit circle all of them. Okay? So before I say what these contributions are, they're very simple. I'll tell that, also have to make a remark that the integral is going to be very simple. It can be made by residues, done by residues. So there is a combinatorial formula for this invariant z hat as well that I'm going to describe. And if you prefer, you can have a combinatorial expression. So. Now, what are the edges and vertices? For every vertex labeled by A, you associate a factor q to some power, which I don't remember, and then corresponding integration variable z minus 1 over z squared. If you have an edge connecting two vertices I and j, you associate to a factor which goes in the integrand zi minus 1 over zi, zj minus 1 over zj. Okay? And that's it. So this is now a well-defined function on such graphs. So now you can go ahead and compute it.
And for vertex number I, this would be zi minus 1 over zi squared, yeah?
Yeah, so this is zi minus zi squared. Yeah, if this is vertex which has variable zi. So, yeah. Thank you. Is it clear? Any other questions?
Where is B?
Huh?
Where is B?
Very good question. So B is actually, yeah, so B is element of the co-kernel of Q. So theta functions have characteristics. And B, so what I'm suppressing here is that there is an offset shift by B. Most of the shifts could be easily compensated by shifting lattice sum variable, but that's precisely where the kernel comes from, so it cannot be compensated. So that's the characteristic of theta function. So I don't want to, today is not going to be important, so I want to kind of gloss over it. So if you want, you can assume that determinant of Q is equal to 1. So kernel is one-dimensional, there is no choice. It's just, you can choose any limit. But this is actually a good point, so thank you. Any other questions? So now this is well defined. We can try to compute it. And first thing we find is, so theorem is that, first of all, this object exists. and is well defined in unit circle. So it's a power series with integer coefficients. The fact that it has integer coefficients is not terribly surprising, because what happens is that you get a huge rational function built out of the graph, and it's convolution with a theta function. So non-integer coefficients will not appear. That's not a big deal. And more interesting statement that it's a power series convergent in the unit disk. Okay. So
It is true for any graph.
yes, that's true for any graph.
Any coloring.
And any coloring, the only thing that what the formula I'm giving you, again for sake of time, is when this is definite. So let's assume that Q is, for example, negative definite. So that's
we need.
for this formula to make sense. But definition exists for general Q. Yeah.
By some other way.
Yeah, by some other way. So the theorem actually applies to this more general case. It's a bunch of properties of this object. So first it says that what kind of object it is. It is a power series in Q, and therefore you should start thinking, okay, so I get something which looks like, I don't know, Q to the delta times C0 plus C1 Q plus C2 Q squared plus dot dot dot, where all the coefficients are integer. So you can start asking questions thinking about it as a modular form. So modular forms have similar Q development. So your first question is, okay, have I seen this Q series before? Do I know it? Okay, so you do your first computation for Poincare sphere, for example. So Poincare sphere is a good example where is negative definite, there is no cokernel, there is nothing to think about. So and what you find is that this guy is so-called mock theta function, or mock modular form, which was mock modular form of order 5, as Ramanujan called it, and that's one of the first series that he wrote in Lost Known books. So it is not exactly modular, but it's a cool modular. It's better. It's modern modular. So if modular forms are subject of the 20th century, then mock modular forms are subject, obviously, of the 21st century. So it's even better. Okay, so it converges. It exists. But second property of this theorem is actually quite interesting. You can play with this definition and show that it's invariant under some operations. So see, in low-dimensional topology, you glue complex things from basic pieces. You build complex artistic structures out of basic Lego pieces. But the way you build it allows some non-uniqueness. So there are certain moves you allow to do which lead to the same result. So this guy that I just defined for you happens to be invariant under the following operation. For example, if you see a vertex labeled by A connected to a bunch of other vertices, you can replace it by vertex labeled by A plus or minus 1 if you connect it to another vertex connected to plus minus 1 and don't do anything else. So that's one operation. There is analogous operation for an edge which connects A1, A2 labels, which are connected to the rest of the graph in some way. And what you do here is you allow to create another vertex and a new edge and change the labels in a similar way that this becomes A1 plus minus 1, plus minus 1, A2 plus minus 1. Okay. Now, it's a not complicated statement to prove. You have explicit expression for the integrand. After all, you can even put it on Mathematica and compute if you want. But even analytically with an integrand, you can show that eliminating integration variables, if you have such vertices labeled by plus minus 1, it actually is invariant under this moves, under the separations. So what I actually defined for you is not a function on set of all graphs. I defined for you a function on set of graphs modular relations. And now something interesting happens. These relations are called Kirby moves. And these are precisely relations on the graphs which you're allowed to make such that three-manifold that we described by a graph does not change. So in three-manifold topology, if you open a textbook, you find that three manifolds can be labeled by graphs modular precisely these relations. So therefore, what I really showed you is that this object is a topological invariant of a three-manifold. So to give a topological invariant means to A, give a prescription how to compute, and B, show that it's invariant under some Rademeister moves, or in this case, Kirby moves.
Sorry, I don't really get where did you use the label A so that when you change A to A plus minus 1, the result changes? Because in
Q.
Yeah, it's this intersection form Q. But yeah. Right, but the rank of Q changes, and of course the integrand also changes because this has the right-hand side of both relations has one more variable to integrate over. So, yeah.
But the integrand last case, for example, changed only by multiple of Q, even if you put plus minus.
So what you're basically doing is starting to derive the statement, correct? Yes. Yes, that's right. So integrand changes in a simple way, therefore you basically collect the most boring residue. So yes, as you can see, as our first row already done, part of this theorem is easy, so there is a couple more statements. So this is not hard, it's actually, it's fun to play with. So fun starts when you ask, okay, what the hell is this? So this is invariant of a three-manifold, and natural question is, have we seen this invariant before? So that's where next statement in this theorem comes in. So these are different parts of statement of this theorem. So this appears to be a new invariant. It's not related to anything that I know directly as a Q series, but if you take a limit where Q goes to root of unity exponential of 2 pi I over k, where k is integer, then this gadget, Q series, does have a limit, and in this radial limit on the unit disk, so this is region Q less than 1, you take a radial limit to some root of unity, and what happens is that here you find Witten-Reshetikhin-Turaev invariant of the same three-manifold, and level k, so k is the level. And the same group G, which for me was assumed to be SU2 as in every other example or discussion that we had. Yeah. So it is.
What about other relational exponents?
So in that case, I have to drop W. So Witten doesn't like these roots because in Chern-Simons theory they make no sense. It would be rational level. So physicists never like this. But Reshetikhin-Turaev made a definition which actually allows that. So it behaves in a way that reproduces Reshetikhin-Turaev. So that's a good question. So by itself, it's not any invariant you can recognize. It's similar to Waffe-Witten partition function. In some, again, cases coincides. But other than that, it's just a Q series. So you get zillions of Q series labeled by manifolds. So that's very much in the theme of what we're discussing. But what's fun and interesting is that now this was a theorem, and property or observation is that in all cases that it has been computed, it's a character of some logarithmic vertex algebra. And we believe that that's a general property. So one case which has been studied really carefully, and that's a case on which this believes, where it originates from and on which it's really based, is the case of fairly simple graphs. which generalizes that example of order 5 Ramanujan mock modular form that I showed you. So suppose you have a graph such that it has labels -1, well, I'll call it A1, A2, A3, maybe assuming that all of them are negative, so for simplicity I'm putting minus here. So then, if you compute this invariant for this guy, what happens is that it's a character of log VOA, which is known. It's called 1, P singlet model. And there is, it's closely related to another model which is called triplet, which also plays a role in this case. And that by itself can be understood as a kernel.
Right, what is P?
Oh yeah, so yeah, that's what I was heading to. So for P equal to A1, A2, A3. Assuming, at least in the case when they're relatively coprime. So for example, 2, 3, 5, 2, 3, 7, and so on and so forth. When they're not coprime, there are some modifications which, I mean, in any case, it's a character of some log VOA, but which log VOA sometimes it's kind of random. So in any case, next question is, okay, if this works, how about more general graphs like this? So with Boris, we believe that this still is true, so we're trying to construct these log VOAs and understand them better. But and they probably can be defined using a construction that Boris introduced with Tipunin of taking kernels of screening operators. So this model is a kernel of 2 screening operators, but if you take more than 2, you can have more general VOAs. But main question that I want to end on is why? So why this happens? This is pretty mysterious, and if in previous case of, say, VOAFM4, I could explain from physics where this vertex algebras appear in correlators that cyber-Quitten invariants compute and so on. There is a physics framework for this. Here it's much more mysterious. And also algebras themselves are much more mysterious. They're logarithmic. But in some sense, this is pretty cool because there is a lot of connection to quantum groups, Kazhdan-Lusztig correspondence, and mock modular forms, all of which form a very interesting package. It's kind of right on the cutting edge in every field. These mock modular forms are cutting edge of modularity. In terms of representation theory, this tensor categories, MTCs associated to the singlet and triplet models are closely related to behavior of quantum groups. They're non-semi-simple, and the story here is quite interesting. Again, that's the part of Kazhdan-Lusztig correspondence and very deep relations between like positive, negative zones and so on. So to me, this is definitely something that's where I have more questions than answers. So therefore, I present it to you with opportunity to, I think anything you can touch here is already in your result, essentially. Thank you.
Can you define G for any group?
So this invariant for any group? Yes, it's well, at least for SUN. So, yeah. So what happened? So far, most of the definition is for SU2. So in fact, it can be defined for any 3-manifold and using other constructions. Recently, we had a paper with Ciprian Manolescu, which does it using surgeries. So it's defined in a number of ways. So now topological nature is well understood. In the case of SU3 and higher rank, it's not so well understood. So people are making just baby steps, as far as I know, and they observed that what you get is higher depth mock modular forms. I have no idea what these are, I just know the names, and I have no idea whose characters are this high rank. So probably I don't know, like high rank singlet, triplet. So great question, but I know very little about it. And I think it is known very little at this point.
Is it possible to understand what are the operators in the original six-dimensional theory which become two-dimensional vertex operators?
Or in this VOAFM4. So these are, I can say physics words. I don't know, again, how to do it mathematically. Well, I know bad mathematical answer. So physics answer is that these are M2 branes wrapped on two cycles of the 4 manifold. They become particles in 2D theory. Mathematically, vertex operators are correspondences acting on moduli spaces, roughly of instantons. But as I've been trying to emphasize all along, thinking about vacuum module of this VOA as cohomology of moduli space of instant is a bad idea. It works only in special examples where some vanishing theorems hold, but on general form, it's a horrible idea. It should be viewed as Floer homology, and in that case, I actually don't know.